talk a little bit about implementing Ruby, JRuby, specifically on the JVM. Some of the challenges we have. Basic introduction. I am a co-lead of JRuby still. Also just kind of do general JVM language stuff, JVM optimization stuff. Kind of a JVM advocate. Was what Sun, then Engine Yard, and now at Red Hot in the JBoss's Polyglot group, where we're doing a lot of fun stuff. So onward to JRuby. JRuby is, you know, Ruby on the JVM. Nothing too fancy about that. We like to think of it as a better VM for Ruby. And, you know, it's kind of a nice language for the JVM. It's a two-part thing there. Mostly implemented in Java. It is pretty much the fastest Ruby implementation. There are, you know, others that are working on trying to beat us at this point. But right now, pretty much the fastest. And it was the first Ruby to actually have real parallel threads, because we got that free from the JVM. It is also impossible. There's so many challenges that we have had to deal with in the process of implementing Ruby and implementing all of its various platform level behaviors and all of its different details in the language itself, that, you know, this shouldn't be possible. And a lot of people told us this is not something you're going to be able to do. It's never going to run well. You're never going to be able to support all of these different features of Ruby, and we didn't listen. So, a little history about Ruby itself and JRuby. Ruby was born in 1993, so the concept of Ruby is actually older than Java itself. I think the first 1.0 version came out around the same time as Java in 1995 or so. JRuby is one of the older JVM languages as well. Actually started in 2001, I think had actual running code, simple Ruby implementation within about a year after that. I joined the project in about 2004, started to work heavily on it in 2005, and then in 2006 we managed to get Rails running, we managed to get a presentation at Java 1, and from there it kind of just ramped up very rapidly once we joined Sun. So why is JRuby impossible? There's a few areas that really have been challenges for us, and many of these remain challenges to this day. I'm going to go into each of these in detail, talk about what we've done to work around them or to solve these problems, and hopefully how the libraries we've come up with and the work that we've done will be useful for you if you run into any of these same sort of issues. So let's start off with a byte array-based string. When JRuby was first designed, Ruby is all mutable strings, so it was originally string was implemented as using a string buffer. And that works reasonably well if you're doing all just text-based data. But Ruby uses the same structure, string, for binary reads out of I/O objects, for writing binary, for doing various types of encoded text. So having only string buffer, which is only UTF-16 characters, was a problem for us. And actually in Ruby 1.9, in the same run of an application, in the same process, you can have multiple strings that all each have are associated with their own encoding. So that you can handle multiple encodings coming and going different locations, transcode across all of those, and not always have not have to force everything to an intermediate format like the JVM does. Debate whether that's a great decision on the Ruby guys' part or not, but it's how it is. It's something we have to support. The other thing about this is that we needed to be able to use the Java APIs ideally. So we stuck with character arrays or string buffers, string itself for a long time, just because we wanted to be able to use those Java strings. But over time, we realized more and more that to represent Ruby strings as Ruby does, we're going to have to use a byte array. And again, this is one of those impossible things. We lose all of the APIs that work with strings directly. We have to do a lot of stuff on our own. But we tried to give it a shot. We wanted to see if we could do this to make it work and make it match Ruby better. So for this, we started out having basically a byte list, which is kind of like a string buffer for a byte array. It allows mutation, it allows slicing, allows copy on write, and it also includes encoding as part of that. So it's basically a byte array-based string with arbitrarily encoded text in it, or perhaps not encoded at all, binary. This is, I think, probably the only one-class Maven project in the world, but it is out there, and you can pull it in if you need a string buffer that's got a byte array behind it. Very simple walkthrough of using it. Works pretty much like you'd expect a string buffer to work. Construct a new one. You can specify a backing store size that you want for it. Append bytes into it. Append other byte lists into it, or individual characters, individual bytes. There are some utility functions for turning Java strings into byte arrays using various different encodings. Getting the copy of the bytes out, or the view of the bytes, which is kind of like the toString on a string buffer, or getting the raw bytes out, which is an operation that a lot of people wish you could do with a string buffer, rather than making a copy every time. And then, we maintain begin and length. Internally in JRuby, we kind of do copy on write operations to avoid the buffers getting recreated too often. But it's a nice little utility class, and hopefully we'll put more of the copy on write stuff in there over time too. So now we have our byte array structure. We have to have something to represent encodings. And for that, we have a project called jcodings. This is basically a set of character tables, character encodings, UTF-8, UTF-16, big end, little end, 32, lots of Japanese encodings, European encodings, more encodings than typically are available on the JVM, and we can support these at runtime in any RubyString, along with the encoding and transcoding of all this stuff. It has information about the character tables, the multi-byte character offsets, how to do searches, character by character searches, and all the different encodings. And this is mostly generated from standard Unicode tables and information about these encodings. From the standard places, we create this, and that feeds into the rest of the system for doing character access and regular expression work. So we get a structure kind of like this for a JRuby string. RubyString aggregates a byte list. The byte list itself aggregates a byte array and an encoding. And then we do some tricks within RubyString to, like a flag to indicate that we know it's all 7-bit ASCII, we know it's all 8-bit ASCII, we know it's all UTF-8, things like that, to avoid doing raw multi-byte character searches when we know we can do random access. And so we're good. We've got our string, essentially, which is a byte array and encoding, but we need things like regular expressions. Like I said, we lose all of those APIs that we have normally on the JVM for strings. So what about just using java.util.regex? Well, of course, we used this with strings back when we were using strings and string buffers. And it worked, and it was free for the most part. But if we're to use that now, we'd be transcoding things to and from string or from character array every single time. And for a while, we did this. We took the performance hit because we knew we needed the byte array strings. But it just really did not scale over time. Too many objects, too much transcoding, and we had to get rid of it. There are also cases in some Ruby applications and libraries where they'll use a binary regular expression. There was a case in a Rails version where they actually were checking for JPEG and PNG headers using a regular expression. That is really difficult to do in Java's regular expression stuff because it expects to be working entirely with character data, and it's all character arrays, so getting the binary data in there in the first place is very difficult to do without mangling it in some horrible way. The other problem with java.util.regex is that it's just broken. There are very simple regular expressions that can cause java.util.regex to blow the stack completely out. And even just get slightly more complex regular expressions, even with not a lot of data, can blow out the stack because of the way it's implemented. And we did run into this. One of those cases was doing regular expression-based parsing of MIME input, which can be arbitrary length. Had a couple alternations in the regular expression, blow the stack regularly. Very easy. I have a blog post about this, and we went through a couple different implementations of regular expressions. JRegex, if you're interested in one that does not have these problems and works pretty well, is probably the best one we found that was character-based. But what we needed was a byte array-based regular expression. We didn't want to have to transcode or copy the data out of our strings every time we were going to do regular expression matches. And so we had to come up with our own. We needed to be able to work with bytes directly. Ideally, we needed to be encoding agnostic, which there's not many regular expression engines that can even do that. We obviously didn't want it to blow the stack, and we wanted it to perform well. And of course, this is another impossible thing. But we had to find a way to do it. So initially, we actually ported from C the regular expression engine that regular C Ruby uses, which was a fairly naive version, only supported ASCII and UTF-8, and it worked pretty well. At least got us off of java.util.regex and character-based and transcoding overhead. Over time, though, we needed to be able to support what Ruby 1.9 uses, which is a regular expression engine called oniguruma. It means like text monster or something in Japanese. But it is actually a large C library for doing regular expression matching on raw bytes with arbitrary encodings and with pluggable grammars as well. This is the regular expression engine that Ruby 1.9 adopted early on, and the only real option we had was to port it. And luckily, the magic of open source, we had a contributor that took a look at the code, disappeared for a month, and came back with a Java port of Oniguruma for us. Just like a gift from heaven. And it was actually faster, more stable, and better than the original one. So, awesome. Yes, yes. So I'd love for this to actually become something that's in Java, maybe replace java.util.regex. So it is a bytecode machine. It will not blow the stack. There are, of course, like any regular expression engine, there are extreme cases where it may run forever, but it doesn't have nearly as many failure cases as java.util.regex does. Having a pluggable grammar is nice. It supports GNU, POSIX, I think Perl, and you can define additional grammars and additional regular expression syntaxes for it if you like. It would be very easy to turn this into a JVM bytecode compiler as well. And then you would actually have JVM bytecoded regular expressions that would run as fast as Java code doing that match directly. So that's something that we're hoping to work on soon. Maybe we can get our friend to reappear and work on that as well. Or maybe one of you would love to do a regular expression compiler. So like I say, none of java.util.regex's catastrophic cases. Arbitrary encoding support. And there's the link for the project on GitHub. So a quick little demonstration of it. One of the big things we need to work on is a better API for it, but you can see the basic structure here. So the inputs here are going to be options for things like multi-line, etc. The encoding you want to use, which is going to be a jcodings encoding, UTF-8, Windows 1252, whatever you want. And then the syntax. There's a few that are built in, and you can define additional ones. So we've got our byte representation of the regex. This could easily come in as a string with an API improvement. And we've got the actual string that we're going to match against. Create a new regular expression with the pattern, the options encoding and syntax. And from here out, it's pretty much like java.util.regex usage. We get a matcher based on a string, and we specify what range of bytes in that string we want to work against. And then we do our matches, our searching, and pull regions out of it to get different groups that we've matched. Very simple and much better than java.util.regex for us. So use cases for this. Obviously, alternative string representations like we have in JRuby is a big one. Anything that you can stuff in bytes, we can match if you give us an encoding and a syntax. That actually kind of opens up some interesting opportunities. Anybody that's using regular expressions to do parsing or matching off of NIO streams, you have to do that. You have to transcode all of that data into characters right now, then do your matching, and then possibly turn it back into bytes if you're going to work with it from there. We could actually work with the bytes directly from this regular expression engine and never have to do any transcoding at all. And in fact, do the regular expression matching in the native encoding of whatever that data is coming as, rather than turning it into UTF-16 at all. Like I mentioned, there's an alternative that's supposed to say pluggable. Alternative regular expression grammars that could be plugged into this. So if you have an unusual grammar that doesn't fit GNU or POSIX, we can look into finding a way to add a plugin or an additional syntax to it. So hopefully this will be useful for other folks. To-do cases. So the API needs a lot of love. It's very raw. You pass in a byte array and a range for the pattern, a byte array and a range for the string, and it can be a little hinky as far as error cases and exceptions. When it works fine. When you have an error, it's a little bit hard to sort out where the parsing problem is. It's not a problem in the engine, it's just a bad reporting mechanism for bad regular expressions. The JVM bytecode backend would be awesome to have because it would really improve the speed of it. It's comparable to java.util.regex even as it is, but having a bytecode backend would be even better. Now we're actually talking a little bit with the Nashorn guys. It would be nice to have this regular expression engine or something similar, something modified, actually be java.util.regex, so that everybody who's doing the same sorts of things, large alternations, more complex regular expressions, would not have the same problems that we ran into. So possibly looking at maybe doing a Joni version that is just character array based, but gives you all the benefits of pluggable syntaxes and the byte-coded engine behind the scenes. So that'd be a fun project. Search and replace. Okay. So the next big area that we ran into is that we needed our I/O layer to basically mimic POSIX I/O. Needed to look like libc I/O operations, because that's kind of, Ruby kind of just wraps all the POSIX functions in a loose class structure. And so for us to be able to match behaviorally, we basically needed to match how libc write and read and different calls at the native level behaved, buffering-wise and whatnot. So blocking and unblocking, need to be able to turn streams from blocking to non-blocking, or have the same calls against the same streams, like you can do with a raw POSIX API. Buffering and unbuffering, and different forms of buffering, like line buffering. Arbitrary encodings, so we need to be able to read stuff in and then apply different encodings to it, or do transcoding on our terms as we read or as we write. And the exceptions that we would get in regular C Ruby often just mapped to the error numbers that would be at the raw POSIX level. So we had to kind of simulate those. We needed to have the same exception structure for people to be able to build Ruby I/O heavy systems on JRuby. Again, impossible to do all this, right? We can't get access to raw POSIX stuff. We can't simulate all these things. But we thought we'd make an attempt at it anyway. So what we came up with is basically a set of POSIXY wrappers around NIO classes. They use NIO channels directly. They do their own buffering. But they allow us to simulate essentially all of the different POSIX I/O behaviors. So we can do things like an fopen that gives us a stream with buffering on top of it. We can do dupes, so we can pretend that one channel is actually in two places at the same time. The buffering characteristics, selection on different types of streams, all pretty much looks like the libc API, which made it simpler for us to duplicate Ruby's implementation of its I/O and file classes. Did spend a fair amount of time reading glibc source. I do not recommend it. But when you got to figure out how it's actually doing the buffering internally, when it's flushing, when it's doing sync operations, there's no better place than the source. And there's really no good libraries for this. You have the standard java.io stuff, which does buffering, but you have to kind of pick the version of buffering they want to give you. You have to deal with the fact that you may have 2 or 3 levels of buffering, whether you actually want it or not. So you can't actually get at raw channels in a lot of cases, and you can't do the buffering on your own terms. And so we had to kind of just build our own stuff. So the first class is channel descriptor. Basically just mimics a file descriptor like API and wraps a channel directly. So this is your open, your read, write, dupe, dupe2, the standard POSIX functions for dealing with file descriptors directly. It wraps a channel, and so in order to do duping, we have a reference counting system. So we know how many different places have a reference to that channel, and then we simulate that we've actually got multiple descriptors available in memory. And then we actually do simulate file numbers or file nodes by having a weak internal table of all the channels and the file numbers that they're associated with. So we can simulate file descriptor numerically even for channels and streams that don't have file descriptors available at the Java API level. ChannelStream is the next level up, simulates a file star in POSIX, the wrapper around a file descriptor with a buffering and whatnot. And so this is your fopen, fread, fwrite, etc. We have the basic buffering modes that you would expect internally. Try to buffer pretty much like libc does. And we do have some support for auto-closing, which, via finalization is not very guaranteed, but it's one of the things that we've added in there to support Ruby's auto-closing, which it does have. Love these implementations with crappy GCs. Okay, so the next level there is actually they'll have the selector logic. We do various tricks to try and simulate selection over all types of channels that we can. For the most part, this only works on sockets and pipes. You can't, for some reason, do selects on standard I/O or process I/O in the Java API. Thanks very much. So we have to do other tricks to kind of fake that stuff. We do also have a pool of these to make sure that we don't burn through selectors too often, but essentially trying to simulate at what we'd have at a POSIX level with just a select call. And then just build it on top of the JVM selectors, which are KQ and epoll and other stuff. So use cases for this. Well, obviously you can have raw NIO level performance on top of this stuff and not have to worry about the buffering characteristics of whatever stream you're using. Better control over how the buffering works and how syncing happens. And if you need this sort of semantics that libc gives you, this is much closer to it than any of the Java I/O classes. All right, some to-dos here. This one has never actually been externalized as a library. There's a few hooks back into JRuby, specifically for managing the file no, the FD table that we have, for managing some of the reference counting stuff. But we can pull it out and make it externally a library if there's folks that are interested in having a very fluid, very flexible buffered wrapper around NIO, essentially. We want to clean up and match libc better. Try and just actually build out all of the different file descriptor and file star functions semantically so they match exactly what libc would do in those cases, but wrapped around channel. Improve the external API. It's kind of grown organically, so it needs a little cleanup. And better select and channel support, which I'll show in a little bit how we're actually going to try and do selects on non-selectable channels. Okay, so more POSIX stuff. Again, like I said, Ruby is largely a language wrapper around a bunch of POSIX APIs, a bunch of C APIs, loosely confederated into a set of classes. But we needed to be able to support a lot of these features to be able to let Ruby scripts run, like getting an actual stat structure that has all of the file system attributes. Now we can do some of this on 7, but not all of those attributes are even still there. Needed to be able to do like a true exec. There are places where people will use Ruby simply to launch another program, and they don't want the original sticking around anymore. So we need to be able to exec and actually kill the parent process off in the process. PIDs, GIDs, user IDs, group IDs, effective user IDs, all the different stuff that you have at a POSIX level for controlling access control and identity and whatnot. We needed to be able to expose those somehow to Ruby users without having access to those APIs on the JVM. Changing the directory of the current process, changing modes and ownership of files. Before Java 7, you couldn't do any of this. You can do some of it now. We can do all of it. Forking. People actually still want to use fork, and they want to be able to fork Ruby processes because Ruby can't run multiple threads, so that's how you get around it. You fork it off, and you do a separate process. We do have a way to fork, but it doesn't work. And then, you know, like I mentioned, selectable standard I/O, process I/O, whatnot. Those are the sort of things. People want to be able to stream data into standard I/O or stream data out of a process and use select operations on it to know when it's ready. Can't do that on the JVM. Cannot. But we have ways to do it. So, impossible. Double impossible, because there's fork in there. Okay, so what we have to solve this problem is called the Java Native Runtime. Is anybody familiar with JNA, Java Native Access? This is way better than JNA. And actually, it's one of the same authors that came and wrote this for us. So Java Native Runtime is a tool for binding native libraries, native code into Java programmatically, without writing JNI, without writing C code or C++ code. Just using regular Java code, you can pull in any C library and bind it to Java functions, essentially. Honestly, I think that not having some sort of FFI layer is a gross, obvious omission from the JVM at this point, especially considering every time they add something that has to access native, we get a bunch more JNI code in OpenJDK that could just be FFI based or native runtime based. But you know, that's a debate to have with other folks. The overhanging project is JNR on GitHub. So if you're interested in any of this stuff, you can find all of these projects there. And it's Apache 2 licensed, so you should be able to use it anywhere you want. All right. So the base project is jffi, which includes the native bindings and a very slim Java layer above it. jnr-ffi is the API you'll probably come in contact with most frequently. It's built on the Java Native Runtime, runs on top of jffi, and it provides a very nice JNA-like foreign function interface to C libraries to native code. Very similar to how JNA works, but optimized for performance. It has support for using Java code as callbacks to C functions. It has much wider platform support, mainly because we've got JRuby users all over the place. I think we're still waiting on an OpenVMS build, but these other weird platforms are supported at this point. Let's take a look at what this actually looks like. So here is kind of a macro-based definition of a bunch of add functions. So add functions across int 8-bit, int 16, int 32, and so on and so forth. So this is a C library that we would want to bind into a piece of Java code. Very similar to how JNA works, we define an interface. We just put pretty much the nominal types of what we want for the inputs and outputs of all these different functions and have JNA loaded up. It wires it up to the appropriate library. Some of that code's not shown here. And then makes sure that all of these functions are bound to the appropriate entry points in the C library. And so in this way, you can pretty much bind any piece of C code, any C library, with just a little bit of Java coding and perhaps a little bit of work wiring up struct sizes and memory locations and whatnot. And we use this very heavily throughout JRuby for a couple different things I'll mention in a moment. Okay, so jnr-posix is one thing that's built on top of jnr-ffi. jnr-posix is an incomplete set of bindings of a bunch of standard POSIX functions like stat, link, symlink, chmod, stuff like that. Already prepared, already properly aligned and properly figured out for several different platforms. So you use jnr-posix on Linux, Windows, Solaris. I think there's the various BSDs are supported. We have it all figured out how the stat structure is laid out, which functions you're supposed to call for different things, and you can call just a single function out of jnr-posix. We do actually have in here a pure Java simulation where we can't do the native versions. So in some cases, we might try to shell out. We might use Java 7 APIs when they're available. Try to do the best job we can to at least have a reasonable fallback when the native stuff can't be loaded. Again, if this was just built into the JVM, we probably wouldn't have to worry about it as much. We're looking to add more. There's obviously a massive number of functions in POSIX that you might want access to, and we've only mapped what we needed for Ruby, but it's very easy to add more, and we're looking for folks to contribute to this. Enforca is unfortunately still impossible because of the way the JVM works, but you can go ahead and call it if you really want to. And segfaults will follow you. Okay, so here is a small sampling of functions that we have already pre-bound and set up to work on various platforms. chmod, exec, like I say, fork is there and doesn't work. Environment modification, getting the current login. There are functions not shown here for getting password entries on systems that have password files. Pretty much anything that you would need to call that the JVM doesn't do, we can find a way to bind it. And notice down at the bottom, we've actually got support for the raw C error nose as well. So if a function fails and the result is not contained in the return value, you can get the most recent error no that happened for your native call and essentially do anything that you would do in C from Java. Getting an instance of it is pretty simple. POSIX factory is part of jnr-posix. You get a POSIX instance by passing in a POSIX handler, and you can try and force it to use non-native if you want. Of course, if it can't load the native stuff, it'll fall back on the Java version anyway. POSIX handler is just a little interface for if you want error nodes to actually trigger exception events, you can implement this to do that. If you have a different way of representing the current working directory, as we do in JRuby, you can implement that. And again, this is just little hooks that we've realized over time we needed to make these calls make sense on the JVM, first of all, and on a runtime like JRuby where we might have multiple instances of it in memory with their own current directories, things like that. Okay, so that's jnr-posix. Now, one thing you're going to run into with a lot of these APIs is that they all have their own constants. And these constants at the C level are not even consistent across platforms necessarily. Some define them, some alias alias one to another. The values are usually not the same for all of the different constants you might have. For example, error nodes may be a little bit different across platforms. Open modes, file modes, FCNTL things, the various constants for socket setup. And so we had to have another project to basically map all of these different constants across different platforms and provide it in a simple way that we could use from Java. Here's an example of one of the pieces of code that it's generated. We periodically will go through and regenerate these on the supported platforms, which I think includes about a dozen different platforms right now, CPU and operating system combinations. This is all the open flags for the file descriptor open2 POSIX function. Read-only, write-only, etc. And these map to what the actual C code would use to make these calls, because we have to have the right values for all these. And notice there's a number of these that aren't actually defined on Linux. If you flip to a different platform, they'll be slightly different. Some of them will be alias to each other, and so on. Notice sync and fsync are actually the same value here. So little interesting details that you can get out of that. So the there's a finite set of constants that we've done so far. FCNTL, open, socket modes, address structures like PINet and AINet and AINet6, those sorts of things. Some of the Unix socket stuff. There's a large set. It's very easy for us to add more. So if there are a set of POSIX constants that you need to access some particular API, we can add it, get our various platform folks to regenerate it, and we're good to go. Okay, so going on to some one of my more favorite projects here, jnr-enxio. So this is like NIO, but it's extended. It's extended native cross-platform I/O. It's even better than NIO, better than NIO2. This is essentially an implementation of NIO, channels, selectors, etc., that is built on top of jnr-ffi. So it's using the actual POSIX file operations. It's using the actual raw KQ or epoll selector implementations, and it's dealing with raw file descriptors at the native level. So what you can't get with NIO, like selectable standard I/O, selectable process I/O, we can do with this. And if we can get the file descriptor for standard in, if we just assume it's in the same place it always is, we actually can do selection on standard in, for example, which you can't do on the JVM normally. So, fun one. A little server. This is actually going to create a little TCP server. So we've got two different forms of the sock address structure mapped using jnr-ffi structural layouts. We've got unsigned 8, 16-bit values and whatnot. And then we pad it just like you do in the native structure. So we've got AF-INET, and this is again coming out of jnr-constants. We want to create an internet socket. We want it to be a stream. And then we bind the various POSIX functions that go along with sockets. Socket, close, listen, bind, accept, and so on. And then the logic inside the TCP server, we give it a port that we want to listen on. It creates a socket on that port using the standard POSIX function for creating a new socket. It sets up the socket address structure, so we know where we actually want it to bind. It binds it to that port and then listens, just like you would do in C code, but this will work across platforms. You don't have to write C, and you have full control over how that file descriptor and how selection logic actually works at the Java level. Okay. There are other fun ones that go along in the JNR family. JNR Unix socket uses extended native cross-platform I/O to have a pre-built implementation of Unix sockets on top of all this stuff, with full selection capabilities and all the typical stuff you'd hope for from a Unix socket. JNR x86 assembly is used internally by either jnr-ffi or jffi, and it is what you think it is. It's basically an x86 assembler written for the JVM to allow you to generate assembly, rebind it back into the system using one of these FFI setups, and call native code, generate and call native code. We're using this right now, or jnr-ffi is using it right now, to basically avoid the overhead of libffi, marshalling arguments across, making sure calls wire up correctly. We do it once in assembly, and then we use that code instead. And actually, the cost of calling a C function from at least Ruby, I don't think Java is as fast for this case, calling a C function from Ruby through jnr-ffi is only about 5 times more overhead than calling it from C. So it's really whittled down. And that's like calling a node, the do-nothing function. So you can actually get considerably good performance calling into C libraries using this stuff. Use cases, hopefully obvious. We have an FFI DSL in Ruby that is just awesome. I mean, I have an example of it in a moment. I'll show you. It's really pretty, and we're actually using the x86 assembly stuff and invokedynamic to bind from the Ruby call site for a native call to a native down call in JNI to the actual target. There's only like 2 hops, really, for us to get to a native library function call from Ruby code. It's faster than Ruby does it in C. Very impressive. So any C library can be wired up. Anything that you want to do that you might have done in JNI before, don't write JNI. Use something like this. Help us improve it. You'll feel better about yourself. And yeah, I mean, never having to write JNI again, that's worth it alone. We wrote JNI once for the FFI bindings. You should never have to write out JNI again. So I wanted to show Ruby FFI just because it is a really, really nice use case of this stuff. Yes, so it's a DSL for binding native libraries, etc., etc. It's by far the prettiest and easiest native binding on the JVM. Here's our little library, a couple basic functions to kind of show different sorts of structures, different sorts of values in and out. And there's the Ruby code for it. This is all that's necessary to bind this particular C library into Ruby code. And at this point, myLibrary.calculateSomething will call the calculateSomething function at the C level with only 1 or 2 hops as far as calls in memory. Very easy. We've got a number of different argument types and return types. There is a syntax for mapping structures that's considerably nicer than what you have to do with JNA or JNR. You know, we can do a lot of sugar in Ruby, but all of this stuff is built on top of the JNR family, and the JNR family is available for any language on the JVM. Okay, so moving on from the POSIX stuff, Ruby is also an extremely dynamic language. It's dynamically typed, of course, and dynamic dispatch all the time, so that can be complicated, but it's not as bad as some languages. All we ever do is look up by name, as opposed to, for example, Groovy that may have to look up by name and the incoming types of the parameters. Ours is always name-based lookup, makes things a lot simpler. Unfortunately, these classes are also mutable. So we can't just do simple dynamic dispatch. We've actually got to track if classes are being changed, patched, improved, quotes, at runtime. So you kind of look at Ruby as basically being a class object is created as a blank slate, and at runtime it's filled with stuff. And method calls happen sometimes while things are being filled, sometimes long after things are filled. So we have to track that as well. We also have closures to deal with. We have data that crosses frames, like if you do a regular expression match, that's a function call, but it needs to set local variables as well, tricky things to do. And we have to be able to do things like eval and evaluate code on the fly. And again, this is where a lot of people said they would never be able to get JRuby performance anywhere near a C-based implementation, and certainly not up to where they'd want to use it. So now, doesn't the JVM kind of do this stuff already? Well, internally, yes. The JVM is very dynamic, and it can wire together pretty much any 2 pieces of code if it can figure out a path from one to the other and optimize it like any piece of Java code. The trick is getting it to realize that all of our plumbing in between a call and a target method can just be folded away and disappear. So externally, before invokedynamic, there was no really good way to do this. There were ugly ways, like generating craploads of little intermediate classes that we do our calling through, but even those had downsides. We were creating a lot more code, it was a much larger surface area for the JVM to optimize, and we never really got to the point of performance that we wanted. So our early version, our initial version, and this is what's actually still running on Java 6, we have something called a caching call site. If you've done any language implementation or dynamic language optimization, we have a monomorphic inline cache. Very simple. Cache is a method and the serial number of the class that method came from at that time. So every time we do the call, we check and make sure the incoming object is of the same type. If it matches, go right through and call the method. We don't have to do all the lookup logic again. So this eliminates the costly hash lookup that we would have before. And I just did a blog post on how bad hash lookup actually can be for performance. But the problem is that it's a single piece of code that every single call in the system goes through. And there's no way that the JVM, in its current form, can inline through that. It can't see that a call to foo going through this caching call site logic and eventually hitting a target method can all be done as one batch operation or one piece of inlined code. So yeah, the Ruby sees the caching call site, which is monomorphic. Great. Caching call site looks up and calls methods for every call in the system. So caching call site itself looks megamorphic. The shape of it is impossible to optimize. So the best we can do with something like this is basically inline the caching call site logic and then have to do the slow logic for all the actual method calls, the method dispatches. And Lambda actually will still have the same problem until they fix it at the VM level. Because for Lambda, you're passing a piece of code in, possibly dozens or hundreds of pieces of code, into an each method or an iterator method. And the JVM is going to see, okay, it's always the same each method, it's always the same iterator method, but when it calls the Lambdas, it has dozens and dozens of them. And it won't be able to optimize all the way through like you expect it to. It's a big problem that the JVM has right now with even anonymous interclasses, and hopefully they'll start to work through that, because we need it too. So what we have today that helps things considerably is invokedynamic. Invokedynamic allows us to define our own protocol for how method calls actually work at the VM level. We basically get called by the JVM when it's going to do that invocation. We give it a piece of code, a method, and then it optimizes. It ignores all the other logic that was done to look up that method, to look up the target code. This is kind of the new golden hammer on the JVM. Pretty much anything that you couldn't do language-wise, there's a way to do it possibly with good optimization using invokedynamic. And at least it'll be simpler than what you'd have to do before. This is on JRuby Master today. We're getting 1.7 out soon. And for benchmarks that we're running, some of them trivial, some of them a little bit more real world, getting 2 to 10 times performance improvement over already being faster than the C implementations of Ruby. So this really does work, and the sky's the limit as far as how the optimization goes. So it's a little easier to see this graphically. We have our switchboard and our lovely switchboard attendant here. So up at the top, we make our call, or a piece of Ruby code makes a call. That's our invokedynamic bytecode. I need to call the toS method on some object in Ruby. At that point, the JVM basically calls back to us, calls to our bootstrap method and says, okay, what code goes along with this method? Can you tell? We have to give it basically a handle to a method somewhere in the system that represents toS on an object. So we do that in the form of method handles. That's the Java lang invoke package. So we get a method handle to our target method somewhere in the system. Now the magic comes at this point. Once we've given that handle back to the JVM, once our bootstrapping process is done, all the rest of this can just disappear. And the JVM can actually optimize this dynamic call, a call that we lazily bootstrapped at runtime, possibly based on runtime types, as if it was a static typed call the entire time. Now this is something that we could have done, like I said, on our own with a lot of tricks, but JVM is doing a much better job of it for us now. Now unfortunately, it's not quite done yet. They did a lot of optimization in Java 7 Update 2 to make this stuff run really fast, but there were a lot of bugs, some issues with it that basically meant that we have to turn off our invokedynamic support on Java 7 currently. The Java 8 builds are improving. I think I have that here. So the Java 8 builds have none of the bugs from 7. They're just starting to work on performance and optimization. I was talking with one of the JVM engineers, and he has patches in hand that aren't in any repository right now that get much closer to matching the performance of Java 7. And, you know, Oracle's hiring if anybody wants to work on the low-level intricacies of the JVM JIT. Now, the next problem we ran into is in using invokedynamic and wiring up these handles, the method handle API is, like a lot of Java APIs, very low-level and kind of cumbersome in some cases. The biggest issue that I had with it is that you were always kind of building backward from an endpoint. You have to get a handle to the target method and then juggle arguments sort of in reverse order back to where you've got your call that you want to wire up to that particular target. So I thought maybe if we had a DSL that lets us build these down, it would be a little easier for me to internalize. And that is the invokebinder library. It is a Java DSL, very simple little API or DSL for building up method handles, but you build them forward. You build them down from the top, from the call site to a target, rather than the other direction, which fit my understanding a little bit better. It's also able to do some type validation along the way that you might not be able to get until you actually do the call of a method handle using the original API. Contributions are welcome. The big thing I'm looking for at this point is tricky patterns from method handles that don't have a good representation in the API. I've got an example of try finally, which is heinous in method handles right now. Okay, so here's an example of how you do this with the standard method handle API, the Java lang invoke stuff. We've got some target handle, which is probably a method somewhere in the system. We want to cast the arguments to all strings. We want to insert arguments into it. And we want to drop an argument off the end. And now you have to actually look at this in terms of the target method having its arguments modified backwards from the target. So what we actually want at the end is a method that takes two strings. One of them has already been put in there. We want the second one to be dropped, use the first argument, and eventually return a string result. It's very difficult to kind of internalize how that's working. You can read backwards, but it still feels a little bit weird. So we have successive wrapping of transformations. It's very functional, but it's also very difficult to follow sometimes. So in the invoke binder, you start out at the beginning with the signature you're looking for. You want it to return a string and take two strings. We don't care about the second string, so we'll drop the 1th argument off of the list. We want the first argument to always be the hello string, so we'll insert into the 0th argument hello. We'll cast it to a particular type and then invoke it. Much easier to follow what's actually happening as far as the handle API goes. And it transforms forward like you would do if you were writing a piece of Java code that took arguments in, made modifications to them, and made an eventual call. Now, I mentioned the example of doing finally logic. Writing finally logic in Java code is fairly simple. Doing it in method handles is a lot of monkeying around. So in invoke binder, we have the post logic that we always want to run in finally cases. And finally cases need to run on normal exit as well as exceptional exit. You can see where it kind of goes, starts to get a little complicated. With invoke binder, since this is a built-in feature that we have as part of building, all you do is say, from this signature, wrap it in a try finally with this post logic, and then do whatever your target call is, or do whatever other transformations you're going to do. So this is actually not part of the standard method handle API, and translates to something much more like this. Because you need to be able to map all the arguments through, you need to be able to inline the finally logic into both the exceptional and non-exceptional paths. You need to be able to handle the return values coming out of the finally in the non-exceptional case. Lots of overhead, lots of hassle to actually do this by hand, just to do a finally bit. And so invoke binder, that's where we can sort of have some of these patterns pre-baked into the API. All right, so we're getting close to the end here. The moral of the story here is that whatever you're doing on the JVM, whatever weird project you might have, never stop trying to do the impossible. These problems are fun to solve. And if you can find a hole through to the JVM itself, or through to native code, or if you have magical open source contributors who will port libraries for you, these things are doable and you can fix them. And at the end of the day, there's really nothing that's impossible on the JVM except fork. Thank you. All right, questions about any of these libraries? Yes, Kirk. Right. So the question's about simulating fork in JRuby. We have thought about that. We could essentially clone the existing JRuby runtime. We have a lot of our own runtime state. Where it gets tricky, though, is if we have already compiled some code into regular native JVM bytecode, we can't clone those call stacks at that point. And so then we're stuck. Because both of those need to continue to execute on their own independently. And there's no way for us to clone running threads. That also affects the interpreter, because our interpreter is basically direct threaded. It goes straight through. If we had a stackless interpreter, we could clone it. But the threads are the problem. Yep. Other questions? Yeah.
Since you have done all this wonderful stuff on NIO and everything, do you have anything similar for SSL or TLS in general, TLS library? Because the NIO TLS handling is kind of cumbersome as well.
Right, for sure.
Almost impossible to get it right and with all the cases.
Right, so the question's about whether any of this stuff is available for OpenSSL or TLS stuff. I know in Ruby, in the Ruby land, there is an FFI binding to libopenssl. That doesn't translate directly into something that you can call from Java without some JRuby tricks. But the structure that it's generating for binding OpenSSL would be available. And for something like the extended native cross-platform I/O, combine that with OpenSSL, and you'd have like real native SSL sockets or TLS sockets without going through a lot of the cumbersome stuff that they have in JSSE right now. We haven't done anything along that direction, but it would be easy to either port the Ruby stuff that's doing that, or just build the bindings.
On JNR, for
Yeah, like there could be a JNR OpenSSL that would basically use jnr-ffi to map in all the OpenSSL functions. Yep. Other questions? Yeah.
Can you comment on how your extended NIO performs compared to NIO in Java 7?
I don't know if I've actually run any numbers on that. It'll probably be slower because the channels are going to have their own raw JNI implementation, and we've got a few layers of overhead. But I can't imagine that when you're dealing with I/O, that particular difference is going to make that big of a deal. Extended native cross-platform I/O does use standard NIO byte buffers on both sides. So the only real difference is the overhead of the extra hops for doing an FFI-like call. So compare that to the overhead of the actual I/O, and it's probably not going to be measurable in most cases. And actually, we were talking with the JVM guys about trying to find better ways to get native calls closer to the JITted output, so that maybe at some point in the future, if this gets internalized in the JVM, or we work with them a little bit more, you might actually just see the open call in the assembly code. Things like that. So it's probably pretty close, but I haven't measured it. And in the cases where it's doing something that's impossible with NIO, it performs much better. Like doing selection on standard I/O, which is still my big bugbear. Other questions? All right. Thank you.